Hello, good afternoon. I see some people are here. I'm going to discuss a couple of things and then do some quiz questions. Can you hear me? Who's here? I just have to set up my iPad. Give me a minute. There you go. I'm here. Who's here? Maria's here. Hello. Marlene sent me some questions that I'm going to look at. First, I want to discuss this portion of the notes. Okay. So this is what we do here. I'm going to talk about this, then I'm going to go to the questions, and you guys can ask me if there's other questions you have. I can do those. So I'll put up some makeup quizzes at I'm going to need more time, so let's say I'll put them up by 6:30 for you to try them. And so makeup quizzes and inference, and I'm going to give you something using formulas 5 and 6. All right. So what I wanted to discuss here is what we're doing with hypothesis testing. This is really an interesting way to look at it. So we function, right, with the idea of the sampling distribution, which, if it's for means and proportions, we fall to the looking at the z distribution, right, because we convert our statistic into number of standard deviations from our best guess, or our hypothesized value. And what we do when we do that is we create this distribution. Oops. We create this distribution, and it could be right, it could be wrong. The point is it's centered around what I'm looking for, the mean or the proportion. And that's really where I want to be, right? Let's say we were wrong. Let's say that isn't, the assumption was wrong. So what would the assumption being wrong look like? It would be the case that there was an actual other distribution that was centered around the true parameter that would be at the center here. And that's really where I want to be. So how can I end up there? Well, I could end up there and know that I'm there if I use this. So I'm just showing you here for the one-sided test, correct? I'm showing you here that I'm testing to see if my value with the hypothesized value as assumed, I'm checking to see if I'm in this rejection region, because that implies that I'm probably dealing with a completely different parameter with a completely different sampling distribution. So to put some terms on this, we also call this region, this rejection region, where I'm checking, for the outliers, or how far away my statistic was. I refer to that region as the type 1 error. Okay, so this is this crossover here, type 1 error, or the alpha that I set. So that's what this is. So these are the kinds of mistakes you can make. You can make a type 1 error where your actual, you're going to reject the hypothesis, however, it could be the case that you're actually on the null hypothesis and rejecting is a bad idea. So given that the hypothesis is actually true, you're rejecting the null and you're allowing for that type 1 error. That's your alpha. The other kind of error you can make is type 2 error. That's where you fail to reject or accept the null. I shouldn't have written that, but you fail to reject the null hypothesis, but it's actually false. Okay, that's the beta. What we're really interested in, the reason why we write this, is we actually want to be able, we want to strengthen our test. We want to make sure that we are rejecting a false null hypothesis. We want to in other words, what we really want to do is increase the power. Power is a measure of 1 minus beta. So these are some of the terminology. I don't test you on any of this, but this is the terminology used around hypothesis testing. Something else I want to talk about. Okay, let's just look here on page 29. I have some questions. If you haven't had a chance to read everything. So what are we saying with levels of significance? So let's say you're reading a report that states a p-value of 0.05. Is 0.05, so I don't know anything, right? I'm just reading a p-value of a report. I didn't read the report completely. I don't know the hypothesis. Without knowing the hypothesis, without reading critically, if I saw this result 0.05, what would I know? I would know that this result, remember the statement, we have to assess the statement. It's always the same. P-value less than or equal to alpha implies we reject the null hypothesis. So let's see. For each of these statements, without having the data, just assessing the results, is presuming they're correct. If you're reading a report and it says that the p-value is 0.045, is this result significant at 5%? Yes, because it's significant if it satisfies this. 0.045 is smaller than 5%. This is when we say the test is significant. I'm not going to be able to spell the whole thing. The test is significant. Trying to write significant. Okay. What about the next one? Or just to stress my point, without even knowing what the hypothesis test is, whether it's one-tailed or two-tailed or any other information, I'm telling you that the test is significant based on the p-value. Okay, so then, next problem. Is the result p-value equals 0.05 significant at 1%? Okay, so what if I change that? By changing that, what I'm doing is making it stricter, harder, right? It must be further away, must be very much more strange for me to reject the null hypothesis. So it's only 1%, 5% was what we usually use, but what if we set it to 1%? We're much more stringent, much more strict. In that case, that result would not be significant. We would fail to reject. So test is not significant. Okay, and finally, if a result is significant at 1%, so it satisfies the very strict requirement, is it significant at 5%? Yes, it is. Yes, it is, right? Because, and the way you can do that is you can say, well, it's smaller than 1%, so of course, if it's smaller than 1, then it's going to be smaller than 5, which is even bigger. Okay, so that's just some practice understanding, interpreting, changing the level of significance. And this is what people reading reports will do. They'll see what the p-value is and make an assessment if that was strange enough a result that it was worthy of rejecting the null hypothesis. So let's see. So those are the problems there I wanted to look at. I did some computer output the other day. We did this together with the t-distribution. I have some topics discussed there. Always remember, the fastest way to do a hypothesis test is for a two-sided test, you can just create a confidence interval. So that's make sure you get practice with that. And really, it's just a matter of practice. Here's an example. This one is where you would make a confidence interval. Try this, making a confidence interval, and get your result. I think I gave you the answer for that. I gave you the answer for everything, as far as I know. And if I don't, just let me know. Maybe. So I have solutions everywhere. Okay, so if you find discrepancies, this is not on the test. This stuff. This is just for completeness, and I'm going to have to cover this material next year. I have to get into this, but this year I'm not going to be testing this. We just changed the prontuario, so I have to include all this extra material, which is all very interesting, and it's not hard. It's just more material. All right. So I'm going to let you work through those, okay? You have a week. You have a week to work on all that stuff. And keep in touch with me and send me problems. I'm going to look at Marlene's stuff now. Oh, sorry. I want to go to pick up Marlene's questions. Pretty sure I put it here, but no, maybe I didn't. Okay, I put it in here now. Called it quizzes. There. All right. That's not it. That's not it. Did I pick it up? I gotta do that one more time. Maybe I have to turn it to a PDF. It won't open. Oh, there it is. Okay, probability problems, STS. So these are some review problems. So I remind you, look at the look at the approximate exam distribution that I posted on the site, and on there you'll see that there are no tests for, there aren't going to be no questions on Bayes on the final exam. There'll be no questions on hypergeometric and Poisson either, okay? I just teach those, but I don't test those in the end. I'll have to do that next year. So probability can be used to interpret the results of a test. So we talked about diagnostic testing, right? Given to determine if a person is using drugs. Suppose we assume that 5% of people are drug users. A test is 96% accurate, which we'll say means that if a person is a drug user, the result is positive 96% of the time. And if a person is not a drug user, the result is negative 96% of the time. So it's a 96% accurate test. So it's specific, both specific and sensitive. So in the positive, it gives you true positives 96% of the time. And it gives you accurate negatives 96% of the time. A randomly chosen person tests positive. What is the probability that the person is actually a drug user? So this is a problem using Bayes. What you need to do is you need to extract the probabilities from here, and then work with what you have, and essentially you're going to count on the relationship that probability of A and B is computed as probability of A times probability of B given A. So this is what we're going to adopt, because we don't know, we haven't heard, there's nothing here about them being independent events. In this case, our A, let me put it in terms of the problem. I'll do that in a second. Let me first finish this, because I could write it like this, or I could write it like probability of B times probability of A given B. I should be able to write it either way, right? It didn't specify which one I'm going to look at first. Both of those should give me the same answers. That's quite powerful, because then I can talk about conditional probabilities for diagnostic tests. Like I did show you some examples, and I gave you a problem to work through for one of the quizzes. So to do this, you need to lay it out with the elements of the problem at hand. So let's talk about A as the test result and B as drug user. So I'm going to use T and D. So the probability that, suppose we assume, okay, let's go through each of them. We assume that 5% of people are drug users. So the probability of being a drug user is 5%. A test is now we're going to introduce the test results. The test is 96% accurate, which means, so it's two things. It means that if, so when I say if, that's the conditional part. If a person is a drug user, the result is positive. So drug user, the result is, the test is positive, and that's 96% of the time. the probability the next part. If the person is not a drug user, the result is negative 96% of the time. So that is the probability that if they're not a drug user, the test should be negative. So I'm going to use bars on top to say not, okay? I could do it with pluses or minuses. I'll just do it with the bar on top. Hope it's not confusing. This is also 96%. So that is your data. That is your information. Those are your parameters. A randomly chosen person tests positive. What is the probability that person is a drug user? So now what I'm doing is asking a question to reversing the condition. Now I'm going to have the results of a positive test, and the question is, what is the probability the person is actually a drug user? So what I want to find is where, let me outline that this means, this is specificity. This is how we call this. This is called specificity. I don't know if you don't really need that for the test, but you need that for life. And this is sensitivity. The other one is sensitivity. So the ability for it to be sensitive enough to detect the test to pick up that the person really has the disease, and the possibility of, not getting, it can actually detect not having the disease, okay? So sensitivity and specificity. And what we want to find is that a random person, the probability that if a person tests positive, that they're a drug user. So you're going to use all that information to figure that out. What's missing? What's missing? You can use, I think it's going to take too long to actually finish this one, but I'm laying it out mostly for you. So you guys can finish this and maybe ask me questions. We can try again tomorrow if you didn't get it. So this, you should be able to calculate this. Because of this property up here, it's true that I can calculate the probability of disease and test and divide it by the probability of the test. Remember, so what I'm doing is going to the subgroup, right, the subpopulation, just the people who tested positive, and out of them, what's the chance of having seen both the positive test and the disease? Now, I don't have that information, but I can expand this using the other version of this formula. Other version meaning putting D as a condition. So I'm going to expand that. Can you see? So I'm going to expand that. So it's just an expansion. Just go step by step, take the information, and then the big thing is twisting, reversing, using this twice. First you use it to lay out the problem, and now I use it to invoke the information I have. I have information on given the person has the disease, the chance of testing positive times the probability of the disease. Aha! You see what I did there? So that's the top now, and then the positive test. Now what's the chance of a positive test? Oh, you can't see that, right? So this is what I do. So this is what I've done. So I've just used that formula twice. Now I can't answer the question because I don't have this piece. I don't have the denominator. So just expand it again. Okay, so I'm going to refer you to, if you don't know where I'm going with this, look in your notes and use Bayes' rule or Bayes' theorem. All right, and expand the bottom, and you'll see you have all the information you need to do that. Okay, you have all the information you need, and I'll bring it up tomorrow. I'll save this, and we'll just fill it in tomorrow. But I want to give you a chance to try that, to finish that problem. I could share this list with you, but these are just the quiz problems online that Marlene sent me. Some people have been asking me for their grades, and I sincerely apologize that it's actually impossible for me to sit and go through and accumulate all your grades, but I opened up the midterm, makeup midterm, so you can see your points, you can see your score, you can tally your score, and you can check on me if I do anything wrong. You know, you have everything because you emailed me your solutions, I have the results up there. You can argue with me after I post the grades. And that will have to be next week, because hopefully before the midterm, the final exam, I can do it. But it's just been a ridiculous amount of work. I really apologize, but we are in unusual times. So hopefully looking at the midterm grade and your sense of how you feel right now, are you able to write this test next week? Are you able to, using all the resources you have, are you able in 3 hours to do something equivalent to solving the mock exam? So you'll get a good sense. If you just go right to the mock exam and start preparing it, I'll put the solutions up probably on the weekend so that you can see your answers. But the idea of the mock exam is that you attempt to solve it and then you answer, you correct it yourself. And we can discuss it. We'll be discussing over the next few meetings anyways. Okay? So it's not for me to do the whole mock exam. I'm just going to solve some of the problems you have issues with. It's for you to complete and then come back to me. So where am I going? I got to open that up again. All right, so let's try the next one. Manufacturer, this is a bin problem, obtains computer modems from 3 different subcontractors, 30% from A, 45% from B, and 25% from C. Past experience has shown that the defective rates for these subcontractors are 3%, 1%, and 4% respectively. If a modem is returned to the manufacturer by a customer because it was found to be defective, what is the probability that it came from subcontractor C? Again, you should have a sense that this is going to be a Bayes problem, right? Because I'm talking about posterior and so the later events versus prior events. So if, using the if a modem is returned to the manufacturer by a customer, so if returned, what's the probability, and it's found to be defective, what's the probability it came from C? So let's set up what we have. So the probability that it's from A is 0.3. The probability that it's from B is 0.45. And the probability it's from C is 0.25. Past experience has shown that the defective rates for these subcontractors are, so defective rates, so that means if it comes from A, the chance that it's a defective is 3%. So I'm just going to lay this up for you, and then you guys get going on it. And the chance that it's defective if it came from B is 1%. And the chance that it's defective and it came from... So I think it's an interpretation issue, right? I guess that's obvious. What do I have? And then what I want to find out is what's the probability, if it's defective, that it came from C. So rather than talking about the results, you know, the outcomes at each of the labs, what's the probability that it came from C if it's in fact defective? So again, it's a Bayes thing where I want to find probability of of C and D divided by the probability of D, and so you have to expand this. You have to expand both because you don't have that information. Right? What you have I've put up here. So you need to expand this. With what you do have. And that is that the probability of C times probability of defective given C. So why am I doing that? Because that's what I have. Okay, so I'm using the form of this, of calculating this probability, right? Because I can write it with the condition on C or the condition on D, but I'm going to do it this way because that's what I have here. So I have this, and I have this, and then I just need the probability, I just need the probability of defective. So, you know, to keep your head around this, it's a mess of numbers. Don't lose sight of where you're headed. You're using the relationships to modify your formula in order to use the parameters you have. Okay, so you have the information on the reverse, so you're going to put that there. As far as defective, the probability of defective, what's the probability of defective? You need to expand this too. How are you going to do that? What's the probability of defective? So I'm going to send you again. I want you to stay awake. I don't want you to blindly be using formulas, so I'm not going to just continue writing formulas. So again, look at the Bayes formula. So I do have quite a few Bayes problems in there. I like to make you practice them, but I don't test them because there's so many other things I have to focus on in the testing. But this is very useful, and I really want to drive the point home. Most importantly for your life is to understand that that you can use conditional probabilities to evaluate diagnostic tests. Okay, the other things you can do with it, very practical in manufacturing, these are also relevant, and you might come across this again. So look at Bayes' rule to find this one as well. Okay, so work with that. Let me know if you get the wrong answer and you have no clue, and I will discuss them. Well, anyway, I'll discuss them tomorrow. I'll bring them up again. Okay, what else did she send me? Okay, so I'm just working through Marlene's exercises if no one has anything else. So these questions are just from the quizzes, and she's numbered them here for me. Okay, 18 major computer companies operate in the U.S. and that 12 are located in in California's Silicon Valley. If 3 computer companies are selected randomly from the entire list, what is the probability that 1 or more of the selected companies are located in the Silicon Valley? Well, overall, so this is a binomial. She's asking me if it's hypergen. I see this as binomial because can I identify X and PK, right? So what is that? X, N, P, and K. So what do? I'm looking at companies. I'm looking repeatedly at companies, and the chance that those companies are from Silicon Valley, I have to put these numbers together, and I can know what that is. I can know P. So that's the first thing that pops out at me. I know P because it's going to be 12 divided by 18. Right? Because that's it. It's 12, and there's a total of 18. So 12 divided by 18 is, I don't like using decimals so much. I prefer fractions when I'm putting it in a formula like this, because then I'm going to lose something in the rounding. I'm not sure how I solved it or which answer I used for the quiz, but you should be able, an approximation, to get the same answer. If I do it with 4 decimal places that I like for binomial and proportion problems, it would be that. And then N, the number that I'm going to pick, I'm going to select 3, right? So that's 3. And then the possibility is that none, 1, 2, or 3 of the companies are from Silicon Valley. And finally, the question I want to answer about this binomial variable is, what is the probability that 1 or more of the selected companies are located in Silicon Valley? So I really want 1 or more. But the fastest way to get that answer is to calculate. So what I want is 1, 2, and 3. But the best way to get the answer is to calculate the probability I really want to get 1 minus the probability of x equals 0. So I'm going to go for the complement of this, and that will give me the answer. How's that? So I think you guys can do this without me. You can finish this. Okay, and answer your quiz. So I guess I shouldn't give you the answer because these are for quizzes and you're supposed to complete those on your own. But that's how you would do that, right? So that is a binomial. Next one, another binomial. For this one, what is the probability that exactly 7 of the next 10 tosses will land on heads? So again, set it up. X and PK. Immediately I see what I have. I know I have, I'm talking about tossing a coin. I'm just tossing 1. So the probability of getting a head, which looks like what I'm interested in, is 50%. I'm going to toss it 10 times, and the possible outcomes are 0, 1, 2, 3, all the way to, well, actually let me write them all. 3, 4, 5, 6, 7, 8, 9, and 10. And what I want out of all those possible probabilities is just exactly 7. So I'm going to calculate exactly 7. And that's what I'm going to solve for using the binomial formula. Okay, so I'm not going to finish it, but that's how you would do that one. And okay, she also sent me some problems about SDS. The weight of bags of a particular kind of tortilla follow a normal distribution with mean 28 and standard deviation of 4. The quality inspector randomly selects 16 of this tortilla chip. What is the probability? So you're going to use formula number 3 on your formula sheet. So you know that X is normal, they tell you, with a mean of 28 and a standard deviation of 4, and then with an N of 16, then that means that the sampling distribution of the sample mean is also the same shape, it's normal, with the same mean, but a smaller, tighter distribution, so that the standard deviation is actually going to be 4 divided by square root of 16, which is 1. Okay, so that's the new standard deviation, remember, from the formula, from formula 3. The new standard deviation is the old one, but smaller. And smaller by a fraction, well, divided by square root of n. Okay, so that over that gives you 4 over 4, which is 1. And then what you want to answer is, what is the probability that the mean weight, so this is the key word, you're working with the mean weight of these 16 bags is more than 29, so you want to answer probability that the mean is greater than 29. And I'm not going to do it, but that's what you want to solve. Okay, so that's the setup there. I'm going too fast. You can slow me down and watch this at your own pace, in your own time. Is this the last one? Yes. Suppose it is known that 55% of students at a large university are female. We take a random sample of 150 from the university to respond to a questionnaire. What is the probability that less than 16%? So this is a problem. It has a heading on it, SDS, but the question is, what is it the SDS of? In other words, which formula am I using from SDS? Am I using formula 2 from the formula sheet or formula 3? Well, since I'm interested in the proportion, I'm talking about formula number 2. Okay, formula 2 from the formula sheet. And the results there will help you. So we know that p hat from formula 2 is approximately, let me do this in a different color. Any comments? I'm looking for comments. You guys just watching me? So formula 2 says that p hat from the theory is approximately normally distributed provided the population is large, which they said here, and that we have the assumptions that that it's approximation as long as this is true, right? This is on your formula sheet. That's 1 minus. So messy. I gotta do it again. okay? You get the point. I can't get that. It's only so much I can do with the stylus. Sometimes the stylus is better, sometimes my hand is better. No, my hand is better. Okay. So these are true since P is equal to 55% and N is 150. Okay, so this is going to be true. So if you go back to the formula number 2 on the formula sheet, the distribution of the sampling distribution of p hat is that it's actually centered around the actual proportion of 55, and the standard deviation we have to calculate as p1 minus p over n square root, and we put it there, and then once we get that, we calculate the probability that p hat is less than 60%. Okay, so that you guys finish that as well. So you have lots of homework here. You have more than enough stuff to do working through the problems. Again, try not to look at the answers. I give you solutions for practically everything. Try not to look at the answers and prepare your own response, and then check and verify with my answers. You'll understand them much better than just reading my answers. That's it. That's it for Marlene's questions. I know I went fast, but having gone fast, the class is over. So if I went slower, I would have gone overtime. Let's see if I can do. See if you have any questions. Is there anything anybody has? Because really it's just a matter of going through these problems, and I can talk about them, but you really essentially have them. Let's see if I can find more output. What I'll do tomorrow is I'll check back with you about those quiz questions, and I will also I guess I can give you some. Well, tonight I'll give you some questions. You can try whether you submit them or not. That's up to you. But I will give you some more problems to try, and we can talk about those tomorrow as well. So we'll have more than enough to talk about for an hour. And then next week on Monday, I will do the mock exam. So you'll have the weekend to work on the mock exam. And I'll post a solution of the mock, I guess, on Sunday night. That's what I'm thinking right now. Here's some output. Here's some outputs, okay. So I don't stress any kind of computer software for this class. But you should be able to interpret output. And then, you know, as you need it, if you have software, statistical software available to you in your work or your home, you'll have no problem using the software, interpreting the results. The most important thing is to be able to interpret results. Plugging numbers in, anybody can do that, right? It's the interpretation that's the most important. And that takes education. So if I look at question number, I guess this is a question about the ovens, number 2. Okay, so manufacturer of ovens is concerned that the dial indicating the oven temperature for a certain model oven is overestimating its temperature. So it's saying it's hotter when it really isn't. 4 ovens of this model are selected at random. The dial on each is set to 300, and after 1 hour, the actual temperature of each is measured. So it's set to 300, but the oven turns out to have, each one has an elevated or different from 300. Just one has 300 measured. Okay. Assuming that the actual temperatures for this model when the dial is set to 300 are normally distributed with a mean mu, we will test the above claim, determine whether or not that the dial is properly calibrated. So what we're doing, we are suspicious that it's overestimating. So that's your keyword here. Overestimating means it must be higher. Remember, whenever we do the null hypothesis, it's always set up the null hypothesis is always set up so that we put the parameter here, in this case mean, and equals. And whatever number we put here, it has to carry to here. It has to be in both places. And what we're saying is we believe it should be, it's set, it advertises that it's calibrated at 300. Don't ask me why I did that. So it's 300. And we are suspicious that it's actually saying, uh-oh, I just realized something. Okay, so the dial, okay, so it's actually 300 in the dial, so I said it wrong before. So the dial needs to be at, the dial is 300. Okay, so I'll read it like this. The dial on each is set to 300. So it's set to 300. It's supposed to be 300, but it looks like it's saying it's higher. It looks like we're suspicious that on average it's giving a higher value. Okay? So that's the null hypothesis and the alternative hypothesis. We take our data, and it's all we have are the data. All we have, and this is again I mentioned, this is usually how it is. You just have a sample with some data. You don't have any prior information. You don't know what the distribution looks like of the dial of the measures of temperature. Okay, this is the first time anybody did this, presumably. You don't have any prior information, so maybe this is being done in the manufacturing plant, and so you have no prior information. When you're in that situation, all you have is a sample. You are going to use formula number 6 because you have no sigma. You have no population information. Okay, so this is the most realistic case. So what you're going to do is you're going to take your data and you're going to calculate X bar and S, and you're going to use them. You're going to test whether the mean that you got is any different from 300, because it should be about 300. And how spread out it is, well, if the data tends to be, we're going to use the data itself to test against it, but the idea is if they're really close together, then you need to be very different. You know, you don't need much to be very different. But if they're really far apart, then X bar will have, like in general or in behavior, then you're going to need a very different, or you're going to need X bar to be much more far away. So this is the presumption that, or the assumption that we make that this is true using the standard deviation that is set. Being far away or being very different from the hypothesized value is all dependent on the variation of the variable itself. So we need to standardize the value and turn it into the number of standard deviations from its mean. And I do that below, and what I get as a result is a statistic, right? Because statistic is a number calculated from a sample. It turns out the statistic I get is 2.45. So this is all my data. This is my information, collapsing it into statistics. S, X bar, even degrees of freedom is a statistic, N is a statistic. These are all statistics. And we compute a t-stat with that. Now what does this mean? This is the number of standard deviations we are away, but for a degree of freedom 3 t-distribution, I don't know, is that very far? Usually, you know, I was saying to you, let's go look at the t-table for a minute to discuss this. So is it far, right? So 1.645 for a two-sided test, for one-sided test. If you're 1.645 standard deviations higher or lower for a one-sided test, when we use the standard normal, then you're going to have a significant test. For a two-sided test, it needs to be 1.96. It needs to be further. And for the t, what about for the t? Let's see. I'm going to go look at the t-table and see what I'm talking about. So for T3, how far do I need to be away at the 95% level? So let's just isolate this here. I'll keep going. So how far do I have to be away? Well, so remember this graph, this chart is for the upper tail, and the upper tails are here. So working with the upper tail, to have 5% in the upper tail, you have to be higher than 2.35 with a degree of freedom of 3 to be considered in the rejection region, okay? So it has to be more than 2 standard deviations away to fall into the rejection region, where we say it's very far and we're going to reject the null hypothesis. But as the degrees of freedom goes up, you don't have to be as far away. Okay, so remembering the smaller degrees of freedom, the flatter the curve, so it's more spread out, so you're going to have to be further away. Anyway, you don't need to remember all those details. It's more intuitive if you understand, there you go. That's my explanation. So we're not that far. The way that I did it, the way that we looked at it, we're at 2.45. We are far enough. Now I have to go back. What did I say? I said 2.353. So yeah, we've surpassed that, haven't we? So we are going to end up rejecting. So let's see. Let's conclude this. Okay, so yes, this exceeds. Now, how we proceed, even though we have a sense that we're going to reject, we know we're going to reject, we need to calculate the p-value. Remember how we calculate the p-value. The p-value is a probability. Oh, I have different numbers here. Now I have to check. What did I do? I think I just transcribed the wrong number, but let me check. 305 happens to be the mean. Is that correct? 305 minus 300 divided by 4.08. I have a few typos, but no one seems to complain because I've had them for years. Maybe they don't get this far. Please let me know if you find any mistakes. So this is the answer. I guess I just transcribed. I must have changed something and then it just got transcribed wrong down there. So this number should be here, 2.45. And if you look up that, oh, I see what I did. I probably just pulled the one from the table. So let's go to the table and see what I did. Nope, that's not what I did. So the answer is 2.3, so it's bigger than, so it's between these two. It's between these two, so 2.45 is between 2.5% and 2.5% and 5%. So that's what I'm going to get from the table, and I'm going to write it down now. That's not it. So that's how I get this. So this is just transcribed wrong. So between 2.5 and 5, which is small, it's unusual. It's so unusual, I'm going to say it's very weird. It would be very strange for us to get a result like that if the null hypothesis is true. It's probably not this null hypothesis. We'll take our chances and bet on there being this being indication that the mean temperature is actually higher. So we say this is the test we lay out, and we do reject, and then we say there is sufficient evidence against the null hypothesis. There is sufficient evidence to support the claim that ovens are overestimating the temperature. And then we can go on to looking at the output just to confirm I asked just to look at the output and confirm what you see here. So what you get out of here is the output. So you're going to see your mean. This is your X bar. This is the X bar. This is S. And this is S over square root of n. And then this is the confidence limit, right? So this is going to be X bar minus T star times sigma over root n. And this is going to be X bar plus T star for 95% confidence interval times sigma over root n. What else? Here's the hypothesized value. So this is mu 0 here. The actual estimate is X bar. This is n. You see everything is here. And then this is your S. Make sure, notice if there's no sigma here. It doesn't say sigma. Sometimes in output it'll say sigma if you actually pre-specify and told it that you had prior information and you knew the population standard deviation. And then the output, looking at the output, which one do we want? Do we want the single greater than test? Yes. So this turns out to be the exact. See, it's nice because we were just saying between 2.5% and 5%, but this actually gives you the number, so that's nice. That's a nice thing about statistical output. Excel will do the same for you. So for the Excel code, I put the Excel code at the top of the Moodle page, so you can find that stuff there. So there you go. That's how you read output. That's how you solve that problem. Try and work through the notes, work through material, keep me posted, send me problems. I'm here for you. We have one more week to go, and let me know if you have any particular needs and you want me to solve particular problems. Otherwise, good night. Good luck on the quizzes. I'm going to post them. Give me until, I'm going to need maybe till 7. I'll post them, okay? So just study. Bye.